Hello everyone, I'm Sibu Meher and today we are going to discuss quantum information processing, and the first part of this lecture series will be understanding quantum information. So before diving into quantum information, let us understand what is classical information. So you might have heard all the classical computers, your phones, your laptops, they use classical bits as the fundamental building block. So what is this bit? This bit we store this bit in transistors, which has two states. One is on state and one is off state. We represent this on state as 1 and off state as 0. So any information, the image, the text, the audios, videos, everything is somehow stored as a sequence of zeros and ones. Basically, every information is stored as numbers, and these numbers are basically converted to binary digits, which is a sequence of zeros and ones. So this bit, we call it as a classical system, and it can have two states. One is 0 and one is 1. So this discrete state of the system is called classical states. We call it classical state. Similar example can be a six-sided die. So you might be knowing that it has six different states. Let's call that 1, 2, 3, 4, 5, and 6. Similarly, a fan switch can have different state. This can be a high, medium, or low state. So let us represent any such classical system as X. So this is our classical system. And all the possible classical states to be in a set, we represent them as sigma, which is a set of all possible classical state. So for the purpose of this discussion, we'll consider this set to be finite and non-empty. So we want non-empty because a classical system having no state is basically of no interest. And there might be a lot of interest of a classical state having infinite states, but here we are going to limit ourselves to finite number of states of a classical system. So for our case, bit case, our system is X, is a classical system, and our sigma is a set of two states, zeros and 1. So if we consider the bit, so let me represent the bit as like this. So it can be either in 0 state or it can be in 1 state, right? When you are looking at the bit or when you are measuring the bit. So here looking at is known as kind of measuring the bit. But let's say there is a bit and you're not looking at it. How do you determine the state of the qubit? Or not qubit, it is bit. So how do you determine the state of this bit? It can be either in 0 state or 1 state. Let me give some probability to the 0 state. So the system being in 0 state to be, let's say, 3 by 4. And the system being in 1 state to be 1 by 4. So what does it mean? That we are assigning some probability. As we are not sure about the state of the bit, we are giving some probability to them. We're thinking that this is the probability that the bit is in 0 state and this is the probability that the bit is in 1 state. For example, let's say you have a coin and we are flipping it, right? Flipping it and not seeing it till we make the prediction. So what is the probability of the coin being in head or tail? We know it. Like if we do this tossing multiple times, large enough times, then we'll get 50% probability of the coin being in head and 50% probability of the coin being tail. Similarly, it's a classical system and we can assign some probabilities if we do not know the state of the bit. But this state, we can represent it as a probabilistic state. Okay, so before going into the probabilistic state, let me introduce some notation called Dirac notation. It is generally used for quantum mechanics to represent quantum states, but here we are going to represent the classical state also using Dirac notation. So let me represent the zero state as like this. So this is called cat 0, and the one state as 1 like this. This is called cat 1. So if we represent these two states as cat 0 and cat 1, then our probabilistic state that we have defined earlier can be represented as 3 by 4 0 and 1 by 4 1. So if you notice that this sum of these two probability amplitude, they amounts to 1. Why is that? Because the only possible states we can have in our system, which is a bit, is 0 and 1, right? Bit can be either in 0 or 1. So the total probability should be 1. So our probabilistic vector, probability vector, also can be represented as a column vector like this, 3 by 4, 1 by 4, and we call it a state, probabilistic state. And the rule that this column vector should follow, that all entries of this column vector should be non-negative real numbers. And this should sum up to 1. Why do we need non-negative real number? Because these are probability vector. So each entry represents some probability, and you cannot have a negative probability. You can have 0 probability, 1 probability, and all the numbers in between. Similarly, this should sum up to 1. That means all these numbers should lie in between zeros and 1. Right? Okay, that's fair enough. Now, we have a state, right? Represented as a column vector. If we want to modify this state to another valid state, we can apply some operation. So if we apply operation to a state, this operation is going to take this state from one state to some another state. So if we represent our state as a vector, column vector, this operation can be represented as a matrix. And this matrix vector multiplication will give us a new state that is modified by the operation, right? Okay, fair enough. Then let's introduce some concept called measuring. What is measuring? So in this case of classical systems, measuring is just observing the state of the system. So let's take the case of bit. We have some probabilistic state 3 by 4, 1 by 4. Sorry, it is 1 by 4. And it is also represented as 3 by 4, cat 0, 1 by 4, cat 1. Now, earlier we were not looking at the bit, so we did not know whether it was 0 or whether it was 1. Now let's look, or we can call measure the bit. In that case, let's say we observed 0, which has a probability of 3 by 4 basically, according to our knowledge. So this probabilistic picture, it doesn't tell us the actual state of the system. The system is either in 0 or 1, but it is not actually in a probabilistic state. The probabilistic state is made from our knowledge or our guesses or belief. So when you look at the system or observe the system, that knowledge or belief changes. So let's say we observe the system to be in 0, then our knowledge becomes that bit is in 0 state with 100% probability and 1 state with 0% probability. In other case, if we find our system to be in 1 state, then our new probability factor will be 0 of 0, 1 of 1. So it will be kind of 0, here it will be kind of 1. So this probabilistic vector that represents our knowledge and belief, and when we look at the system or measure the system, that knowledge and belief changes and we get a definite state, which is basically called a standard basis in this case. What is standard basis? In the case of bit, we have two standard bases, 0 and 1. And we can represent 0 in form of column vector as 1, 0, and 1 we can represent it as 0 and 1. Okay, so our probabilistic vector 3 by 4, 1 by 4. That's why we are representing it as 3 by 4 of 0 and 1 by 4 of 1. Okay, now let's go to the other concept called deterministic operation. So, when we apply a deterministic operation, the result is completely determined by the input without any element of chance or uncertainty. So let's consider a state A, which belongs to set of all state for the classical system. And when we apply a deterministic operation, let's say it converts to FA. So this F is an operation that takes the element of this set sigma to another element of the set sigma, or maybe the same element. Let's take an example. Let's consider our usual example of bit. Then our sigma becomes 0, 1. Now we can have four possible operations, such operation that acts on sigma to sigma. So let's name them as F1, F2, F3, and F4. Let's define them. Let's define F1 first. So let's say we have A, and when we apply F1, it becomes F1A. Similarly, we have A. When we apply F2, it becomes F2A. Similarly, A to F3A, A to F4A. Okay, so what can be the possibilities? Let's say A can be either 0 or 1. Right? So in the first case, let's say 0 goes to 0 and 1 goes to 1 because of the operation. The second case, let's say 0 goes to 1 and 1 goes to 0. In the third case, let's say 0 goes to 0 and 1 goes to 1. And in the fourth case, let's say 0 goes to 1 and 1 also goes to 1. So these are all the possible cases that can occur, right? So if we represent our, so this is our 0 state means it is cat 0 and 1 state means cat 1, right? And we are representing our cat 0 as 1 0 and our cat 1 as 0 1. So let's try to guess the matrix form of these operations f1 to f3, f4. Let me write those matrix form as m1, m2, m3, and m4. So if you write m1, it will be like 0 is going to 0, so it will be 1, 0. 1 is also going to 0, so it will going to 1, 0. M2 will look like 0 is going to 1, so it is 0, 1. And 1 is going to 0, so it will be 0. So it's a NOT operation. It's flipping the bit, right? It's a constant operation. It's not doing anything. Everything it is just making it 0. Similarly, this is also a constant operation. And this is an identity operation, right? It is keeping the element same, 0 to 0, 1 to 1. So these two are kind of balanced operation because number of zeros and ones in each side is similar. Similarly, M3, you can write it as 0 is going to 0, so it is 1, 0. 1 is going to 1, so it is 0, 1. Then M4, 0 is going to 1, so we can write 0, 1, and 1 is going to also 1, 0. So these are the metrics from all these four operations. So you might be wondering how am I writing this metric so easily. So let me tell you a trick. So let's say you have a lot of orthogonal basis vectors. Let's say three uh, orthonormal basis. Let's say 1, 0, 0, 0, 1, 0, and uh, 0, 0, 1. So let me represent it as 0, this whole thing as 1, and this whole thing as 2, right? And now let's say I have an operation O1 that is taking my 0 to 0. So all my operation will have a matrix form of 3 cross 3, right? Then only if you have a matrix of 3 cross 3 and you multiply a matrix of 3 cross 1, it will give a matrix 3 cross 1, right? That's what we want, right? We want to convert one state to another state. So whatever this matrix form will be, let's index them as 0, 1, 2. So let's say that this is our 0 column, 1 column, and 2 columns corresponding to the 0, 1, 2. And when this 0 is going to 0, what does that mean? And let's say 1 is going to 1 and 2 is going to 2. So this is our identity operation. This is our 0 and it is going to 0. So we have to write the output vector in the input place. This is how we give the input place 0, and we write the output vector is also 0. We write 0, 1, 0, 0. Similarly, this is our input vector. Now our output vector is also this. Similarly, our input vector is 2 and output vector is also 2. So we'll write the output. But let's take a different case. Let's go 0 is let's say going to 1, 1 is going to 2, and 2 is going to 0. It's kind of rotation, right? So let's apply the same trick here. So here we have 0, 1, 2, and our 0 is going to 1. So in place of 0 column, we write the ones vector 0, 1, 0. In place of ones vector, we write twos vector 0, 0, 1. In place of twos vector, we write the zeros vector. So if we multiply it with any of this vector, we'll get this kind of relation. This is the trick. That's how we find out all these metrics. But there is another way of doing it. So let me tell you that. So while introducing Dirac matrix, I didn't tell you another thing. We were calling it cat, right? These are cats represented as column vectors, right? Column. But when you do the transpose of this, so in quantum mechanics, you basically do transpose conjugate, right? Or dagger. You might have heard this thing. So basically, we make the column to row and we take the complex conjugate of each of the elements. So, okay, let's not go into this. Let's stick to the classical case. So here, if we see, this is how we represent a bra. So this is called bra. And these two kind of this kind of notations are called bracket notation or Dirac notation. Bra and cat notation. Okay, so let's say, so this is our 0, no it is 1 0, then our bra 0 will represent as 1 0 as a row. Similarly, our one cat is 0 1, so it will be represented as 0 1, right? So you can also define some multiplication. So you can multiply this bra and cat. Let's say you are multiplying 0 and 0. It will give you 1 0 1 0, right? So if you do the matrix multiplication, it is 1 into 1 plus 0 into 0, giving you 1. You multiply 0 and 1, so do it yourself. It will give you 0. If you multiply 1 and 0, it will give you 0. You multiply 1 and 1, take the inner product. This is called sometimes called inner product when we are doing quantum mechanics. We will get 1. That's why this 0 and 1 are called orthonormal basis in quantum mechanics. So we can call them here also orthonormal basis. And earlier we are calling them standard basis, right? That means when you take the inner product of the same between the same state, same basis state, you will get 1, otherwise you will get 0. That's why they're orthonormal. Ortho means it's the perpendicular, normal means they have magnitude of 1. Okay, so this is the inner product, and there is something called outer product. So that's this how we do it. Let's say you take the outer product of 0 and 0. First is your column 1 0, second is your row 1 0. So if you do the matrix multiplication, you'll get something 2 cross 2 here. It will not get 1 cross 1, which is a scalar. So you are going to get 2 cross 2. So this is 1, this is 0, this is 0, this is 0. This is the matrix you'll get. Similarly, you can get this matrix for, let's say, 0 and 1. 0, 0, 0 is done. So you can get it for 1 and 1 and get it for 1 and 0. These are 4 outer product that you can get. So the idea is that we can represent any deterministic operation. So here we're talking about deterministic operation, which takes one of the basis state to the another basis state. It doesn't deal with the probabilistic state. That means it does not take one state to some probability state. Like probabilistic state is basically chances and uncertainties. Like we discussed here, this state we do not know what it is, right? Yeah, basically it is a combination of both the state. So we are uncertain with what the state is going to be. So that's the uncertainties come into picture. So any deterministic operation can be represented as summation. So this is a summation of the sigma, where A belongs to that our sigma, and we just multiply or take the outer product of FA with A. So this gives us the matrix form of any deterministic operation. So one more short trick that we can discuss here. So while finding that thing 0 0, what you can do, it is going to be 2 cross 2 matrix, right? So you go to 0 0 position and put a 1 there, 0 0. Similarly, the same trick can be applied here. So go to the 1 1 position, which is here, put a 1 there, another place 0. Only if we go to 0 1, this is the position, or this is not the position actually. Let me delete it. Okay, so yeah, so this is the position basically 0 0 0. and 1, 0, right? So it is going to make 1 here and 0 in other place. So if you see, all these four vectors are basically putting 1 in each of the places and then putting zeros in other places. So it is very easy to guess that we can make any kind of matrix by taking a combination of them, right? By taking proper, proper coefficients. So what is happening here? Let's say you are applying some B to this. B is another, basically A also belongs to sigma and B also belongs to sigma, let's say. So if you apply B, it is going to multiply B to this whole thing. If A going to multiply B to this whole thing. Now, as you know, matrix multiplication is associative. So you can multiply B to each of the elements of the summation. So we can multiply B here. And as we know, A and B both are standard basis, right? They both belong to the standard basis. That means this A, B will be 1 when A and B are equals, and it will be 0 when A and B are not equals. So in this case, only one term will survive when A equals to B. So we'll get FB cat and B, right? So this will become 1 and we'll get FB. So as we know the rule, this N basically takes B to FB. That's what we defined earlier, right? So F is the function that takes one element from sigma to sigma. In this case, B to FB. If it was A, it will take it to FA. So this represents the functional form and M represents the matrix form. So that's the idea. So any matrix form of the operations, we can represent them as summation of these outer products. So let's consider one of the matrix. Let's consider, let's say, N4. And it is, let's say, 0, 0, 1, 1. So which are the matrix that we are going to use here? So if you see, we're going to use 0, 1, 0, 0 plus 0, 0, 0, 1. So if you see what is the outer product here, so this is our 1th position, 1 and 0 position, right? Row and then column. So row is 1, column is 0. Only here 1 and 1. So 4 can be represented as the outer product summation of 1, 0 and 1, 1, 1, right? So that's it. So this concludes our deterministic operation. Now we'll go and see probabilistic operation and stochastic matrix. So let me go to home, no, I don't need to go to home actually. I can create some new slides here so that I can write. So our next topic is probabilistic operations and stochastic matrix. Okay, so let's consider some operation M, which is in the matrix form, by the way, and let's consider some peculiar properties of this M. When you apply M on 0 state, it gives you 0 state. However, when you apply M on 1 state, it, let's say, gives you a probabilistic state which has a 50% probability of being in 1 and 50% probability of being in 0 state. So such kind of operation is called probabilistic operation. Probabilistic operation, and we represent them as stochastic metrics. So let's try to get the matrix form of this operation. So we can represent M as. So now remember the trick that we discussed. We can so 0 is going to 0, so we can write it as 1 0, and 1 is going to half and half, so we can write this half and half here. Okay, so this is a stochastic matrix. So what are the properties of the stochastic matrix? The first properties is that all entries again are non-negative real numbers, and the second property is that the entries in every column should sum up to 1. Did we make some mistake while defining deterministic matrix? I don't think so. Okay, so I didn't define deterministic matrix basically. So what are the properties of this deterministic matrix? So again, each column should have at least one one. That's it. Should have only one, I guess. You cannot have multiple one because it will sum up to some different numbers, which we do not want, right? Only one one. I think that's the properties of a deterministic matrix. Okay, fine. Now let's go back to stochastic matrix. So the work of this stochastic matrix is that it takes one probabilistic vector. So basically, you can represent any probabilistic state as a probabilistic vector, as we have discussed earlier. So if we apply stochastic operation, probabilistic operation, or the stochastic matrix, it is going to give you another probabilistic vector, right? Further, we can represent a stochastic matrix as random choices of deterministic matrix. Random choices of deterministic matrix. So as you just discussed before, a deterministic matrix can only have one in the column. So we can write this M as summation of half. There is a 1 here. So write 1, the 0, 0, 1 plus half of 0, oh 0 should be 1 because then only we can get a 1 there because half plus half will be 1. Then there is another 1 here, 0 and 0. This half will stay, this half will stay, this half will give us 1. These are two deterministic matrix or deterministic operation that you can sum using some fractional coefficient, which basically gives the random choices of deterministic matrix, and we can get this stochastic matrix, right? Okay, next we'll discuss another concept related to stochastic probabilistic operation, which is called composition. So let's say we have a classical state X and sigma, capital sigma is the possible number of classical states or set of possible classical states. And let's say M1 to Mn be the stochastic operation, probabilistic operations, stochastic matrices, and let's U represent a probability vector representing a probabilistic state. Then let's say first we apply M1 to U. This will give us M1U. And if I apply M2 to this whole thing, this will give me M2 times this thing, right? Now, as you know, matrix multiplication is associative. That means we can write it as M1, M2, M1, U. So instead of applying M1 first and M2, what we can do, we can take the multiplication of M2 and M1, then apply it to U. It will give us the same thing. This is possible because of associativity of matrix multiplication. But we cannot change the order here. We cannot write it as M1, M2, U. It is not equals to M2, M1, U. It is not equals. Got it? Because matrix multiplication is not commutative. So the important thing is ordering is important. And if we are maintaining the order, we can multiply the matrix and directly apply it to the probability vector. Now let's prove it. Let's take M1, which is 1, 1, 0, 0. Let's take M2, which is the NOT operation, 0, 1, 1, 0. Now let's multiply M1 and 2. So it is 1, 1, 0, 0. This is 0, 1, 1, 0. Multiply it till 1. This is 1. This is 0. This is 0. We multiply M2, M1. This is 0, 1, 1, 0. 1, 1, 0, 0. This will be row and column. So it is going to be 0. Row and column. This is going to be 0. Column, row and column. Do 1. Going to be 1. So these two matrices are not equal. That's why it is not commutative. This is a well-known thing in linear algebra, right? So this concludes the discussion on classical information. So in the next class or maybe next video, we're going to discuss about quantum information. Thank you for your attention. And by the way, this is my first video, so I might be blubbering a lot. Maybe I might be eating some words, so you might not be able to understand some of them. But I'll keep updating these lectures later once I make better one. So yeah, please bear with that. And yeah, this is for my practice purpose, and also I have heard that the more you teach, the better you learn. So if you want to learn something, you just teach it. So this is an effort in that direction. So I keep learning different things from different resources. So I'm planning to use YouTube as a platform to express my ideas, my understanding, and make it more solid. So that's all. Thank you for your attention, and let me stop it here.